Hi, Ethan. Going on to part C here, we want to write a, we want to uh, predict what gamma should be here for this radius expression, and then we want to write an equation for phi in terms of m, little m, and c and alpha. All right, so I'm going to write an equation for phi, and we want to figure out what gamma will be. Now, I used chapter 4 to get a good guess at what gamma will be, and here's what I mean. In chapter 4, where did I put that? Is that here? Is that here? It's right here. So in chapter 4, there's a figure. This is the radius of gyration for a polymer made of DNA, and this n is a number of base pairs, and that's proportional to the number of monomers that are making up this polymer. This polymer is on a log plot, so this is log of r, and this is log of n. And they don't show you the regression equation here, and they don't show you the math that they've done, but when you do the math, and you from the linear regression equation of that line, you end up with, in this detail, it says what you end up with. You end up with that the radius is proportional to n to the 3/4 power, or n to this power experimentally. So because they found that n to the 3/4 power is reasonably accurate here, I'm going to hypothesize that also in part C, if we say that the radius of some sphere swept out by a random polymer is equal to a l n to the gamma power, I'm going to say that gamma should be something like 3/4 because of chapter 4. Now we need an expression for phi. How can we get an expression for phi here? Well, we know that phi is the volume fraction occupied by the polymer. So it's the volume of the polymer divided by the volume total. Right now, we know what the volume of the polymer is. It's going to be 4/3 pi r cubed, where this is r. So 4/3 pi, this is r. We're assuming that gamma is 3/4 pi r cubed, 4/3 pi r cubed over Vt. But you see, this is the phi if there's only one polymer, but there may be more than one polymer. So there may be actually n polymers here, right? Well, maybe not n, but because n is not the number of polymers. Remember, n in this problem is the number of monomers that make one polymer, right? So there could be a lot of polymers here, and the polymers that are here are enumerated by the concentration, where this concentration is a number concentration. So the concentration C is the number of polymers, I'll call it number of polymers, divided by the total volume. And how do I know that? Well, it says in here that the constant, well, not here, sorry, it says in the problem here that the N, that the polymer is C such, so right here, the letter C, such spheres per volume. So we're talking about C polymer spheres per volume. So C is polymer spheres, the number of polymers per volume. All right, so what I want to multiply here is the number of polymers. So the number of polymers is equal to C times Vt. C times Vt. So instead of number of polymers, I can substitute C times Vt in there. So instead of this, I can put C times Vt. That's convenient because I don't know what Vt is, and now I don't care what Vt is because the Vt's cancel. Even if I have something wrong here, I think it's useful to know that the VTs are going to cancel, so we could use them as a conceptual crutch until they do cancel, in which case we don't have to worry about them anymore. So far I have phi equals now, excuse me, I'm going to get rid of this pi and this 3 because pi is 3.14 and 3 is very close to 3.14, so I'm going to just get rid of them as a rough approximation. So I've got 4 alpha cubed L cubed n to the 3 times 3 fourths is 9 fourths power times c. That's it. That's what phi is. That's what I've got for phi. So that is part C. Now part D, I'm less sure about part D now. So part D is a discussion of the experimental data. All right, so first of all, the y-axis is this thing, which is defined as this thing, where this rho is the mass of dissolved polymer per volume of solvent. Okay, so that kind of makes sense because of the units that are of the graph. So the units of the y-axis are volume over mass. Units of the x-axis are molar mass. This is the mass of 1 mole of the polymer. All right, so oops. All right, so the, volume over mass. That's the y-axis. So let's as part of a discussion of the experimental data, let's figure out what this means here. This y-axis. What does this mean? So eta prime minus eta over eta times rho. All right, so this is part D. So the y-axis equals eta prime minus eta over eta times rho. All right, and rho is the mass of all the polymer over the total volume. Right. So what I've got here is this stuff divided by rho. Now remember that this stuff has a certain simplified version, which we did in part B. It's just, so this stuff is just minus phi, according to this work over here. So if that work is any good, then I can just say that this is minus phi over rho. All right, now that's going to mean that the y-axis is a reciprocal of density, of some type of density. And that's accurate because density is mass over volume, and the y-axis is actually not mass over volume, but volume over mass. So it is the reciprocal of some type of density. So that's what I think we should think of as the, that's what I think we should think of as the y-axis. So that is as far as I got with the discussion of D. So I'm going to make a separate video if I get any further with D and E, the rest of D and E.